Imagine waking up tomorrow to headlines across every major network in the United States. A star so large it would swallow our solar system discovered in the Milky Way, not in some distant galaxy billions of light years away, not at the edge of the observable universe, but right here, in our own galaxy. A star so unimaginably vast that if you placed it where our sun is right now, it wouldn't just scorch the Earth. It wouldn't just engulf Mars. It would expand past the orbit of Jupiter, stretching almost to Saturn, consuming everything humanity has ever known in a single roiling sphere of superheated plasma. No Grand Canyon, no Pacific Ocean, no Rocky Mountains, no New York skyline. All of it gone inside one star. This isn't a sci-fi movie concept dreamed up in Hollywood. This is real. And its name is Stephenson 218, the largest star ever discovered in the universe, at least in our observable cosmic neighborhood. Tonight, we're going to travel 20,000 light-years across the Milky Way into a dense stellar cluster hidden behind curtains of cosmic dust, where this red hypergiant quietly defies the laws of physics as we understand them. We're going to unpack how something this massive can even exist, why scientists almost missed it entirely, and what its existence means for the future of stellar astronomy. Because when a single object can hold billions of suns inside its volume, you're not just looking at a star. You're staring at the limits of nature itself. Before we dive in, if you're fascinated by mind-bending discoveries like this, take a second to subscribe, like the video, and join this growing community of curious minds. It genuinely helps the channel reach more people who love science as much as you do. And I want to hear from you. Drop a comment telling me which part of the United States you're watching from. East Coast, Midwest, Texas, California, somewhere in between. Let's see how far this cosmic journey reaches across the country. To understand just how extraordinary Stephenson 218 truly is, we first need to recalibrate our sense of scale. Most of us grow up thinking the sun is enormous, and it is. With a diameter of about 864,000 miles, you could line up roughly 1 in 9 Earths across its face. It contains 99.8% of all the mass in our solar system. Every planet, every asteroid, every comet combined accounts for less than a fraction of what the sun holds in its gravitational grip. The sun fuses about 600 million tons of hydrogen into helium every single second, releasing energy that has powered life on Earth for nearly 4.6 billion years. By any human standard, it is colossal beyond imagination. But in the broader cosmic context, the sun is actually a very average, middle-aged, medium-sized star. A G-type main sequence star, sometimes called a yellow dwarf. In fact, astronomers classify it as unremarkable. Now consider this: if the sun were hollow, you could fit about 1.3 million Earths inside it. That number alone feels overwhelming, but Stephenson 218 makes that figure look trivial. With a radius estimated at roughly 250 times that of the sun, this red hypergiant's diameter would span nearly 2 billion miles. If you placed it at the center of our solar system, its surface would extend beyond the orbit of Jupiter, possibly approaching Saturn depending on orbital positions. The asteroid belt, vaporized. The gas giants, engulfed. Every spacecraft humanity has ever launched, instantly erased. But size alone doesn't tell the whole story. Stephenson 218 belongs to a rare class of stars known as red hypergiants. These are among the most massive and luminous stars in existence, representing a late and unstable phase in stellar evolution. To understand how a star becomes this enormous, we need to step back and examine how stars form in the first place. Stars are born inside vast molecular clouds, cold, dense regions of gas and dust scattered throughout galaxies. These clouds, often called stellar nurseries, are primarily composed of hydrogen, with traces of helium and heavier elements. Over time, gravity pulls regions of these clouds inward. As material collapses, it heats up, forming a protostar. When the core temperature becomes high enough, around 10 million degrees Celsius, nuclear fusion ignites. Hydrogen atoms begin fusing into helium, releasing enormous amounts of energy. That outward pressure from fusion balances the inward pull of gravity, creating a stable main sequence star. For stars like our Sun, this balance can last billions of years. But for extremely massive stars, those born with perhaps 20, 30, or even 50 times the mass of the Sun, the story unfolds very differently. Massive stars burn through their nuclear fuel at a staggering rate. The more massive a star is, the hotter its core becomes, and the faster fusion proceeds. It's counterintuitive, but bigger stars actually live shorter lives. While the Sun may shine for about 10 billion years, a hypergiant might last only a few million. Stephenson 218 is believed to have started its life as an extremely massive star, possibly more than 40 times the mass of the Sun. Over millions of years, it exhausted hydrogen in its core and began fusing heavier elements, helium into carbon, carbon into neon, neon into oxygen, oxygen into silicon. Each stage occurs faster than the last. Eventually, the core swells and the outer layers expand dramatically. The star becomes a red supergiant, or in even more extreme cases, a red hypergiant. As the core contracts and heats up, the outer layers puff outward, sometimes reaching sizes that defy theoretical expectations. The star cools at the surface, giving it a deep reddish color. Despite the cooler surface temperature, often between 3,000 and 4,000 Kelvin, the overall luminosity remains immense because the surface area is so vast. Luminosity depends on both temperature and surface area, and when your surface area is billions of times larger than the Sun's, even a cooler temperature can produce mind-bending brightness. Stephenson 218 resides in a cluster known as Stephenson 2, located in the constellation Scutum. This cluster lies about 20,000 light-years from Earth toward the inner regions of the Milky Way. The area is heavily obscured by interstellar dust, which blocks visible light. For decades, astronomers had limited visibility into this region. It wasn't until infrared astronomy advanced significantly that researchers could peer through the dust and analyze the stars hidden within. Infrared light has longer wavelengths than visible light, allowing it to pass through dust clouds that would otherwise obscure our view. Telescopes equipped with infrared detectors revealed that Stephenson 2 was home to an unusually high concentration of red supergiants and hypergiants. Among them, one stood out dramatically. Spectroscopic analysis, studying the light spectrum emitted by the star, allowed astronomers to determine its temperature, luminosity, and approximate radius. The calculations were astonishing. This wasn't just another large star. This was potentially the largest known. But measuring stars at such distances is extraordinarily difficult. Astronomers cannot simply stretch a ruler across the galaxy. Instead, they rely on indirect methods. By analyzing the star's brightness and estimating its distance, they calculate luminosity. Then, using the Stefan-Boltzmann law, a fundamental equation in astrophysics relating luminosity, temperature, and radius, they derive the star's size. Even small uncertainties in distance or temperature can significantly affect size estimates. That's why scientific humility is essential. While Stephenson 218 is currently considered the largest known star, future refinements could adjust its ranking. Still, even with margins of error, we are dealing with something that dwarfs nearly every other known stellar object. For comparison, consider Betelgeuse, the red supergiant in the constellation Orion. Betelgeuse is already enormous, with a radius roughly 700 times that of the Sun. It has captured public attention due to its dimming events and its eventual fate as a supernova. Yet Stephenson 218 is estimated to be nearly 3 times larger in radius than Betelgeuse. Then there's UY Scuti, once thought to hold the size record. UY Scuti's radius is estimated at around 1/700 times that of the Sun. That alone seemed almost incomprehensible. But Stephenson 218 pushes even beyond that boundary, crossing into territory where astrophysical models begin to strain. So how can a star grow this large without tearing itself apart? The answer lies in the delicate balance between radiation pressure and gravity. In extremely massive stars, radiation pressure, the outward force generated by photons escaping the core, becomes incredibly strong. At some point, this pressure can overcome gravity and blow off the star's outer layers. This sets what is known as the Eddington limit, a theoretical maximum luminosity a star can achieve before radiation pressure drives material away. Red hypergiants like Stephenson 218 exist near or possibly beyond this limit. They are unstable, shedding mass through intense stellar winds. Observations suggest that Stephenson 218 is losing mass at an extraordinary rate, ejecting vast shells of gas into space. These ejections enrich the surrounding interstellar medium with heavy elements, carbon, oxygen, silicon, the very ingredients that will one day form new stars, planets, and perhaps even life. In that sense, stars like Stephenson 218 are both destroyers and creators. They are nearing the end of their life cycle, yet their violent deaths will seed the galaxy with the building blocks of future solar systems. Massive stars eventually collapse under their own gravity when iron accumulates in their core. Iron fusion does not release energy, it consumes it. Without outward pressure from fusion, gravity wins. The core collapses in a fraction of a second, triggering a supernova explosion so powerful it can briefly outshine an entire galaxy. What will Stephenson 218 become? It may explode as a Type II supernova, Or, depending on how much mass it retains, it could collapse directly into a black hole. Given its immense size and mass, many astronomers suspect it will leave behind a black hole, an object so dense that not even light can escape its gravitational pull. And here's the unsettling part. We are witnessing this star in a fleeting cosmic moment. Red hypergiants represent a brief phase in stellar evolution, perhaps lasting only tens of thousands of years. In astronomical terms, that's the blink of an eye. The fact that we exist at a time when Stephenson 218 is in this phase, and that we have developed the technology to detect and measure it, is extraordinary. When you look up at the night sky from anywhere in America, from the deserts of Arizona to the forests of Maine, you're seeing only a fraction of what's truly out there. Hidden behind dust clouds and vast distances are objects so enormous that they challenge the boundaries of imagination. Stephenson 218 is not just a record holder. It's a reminder that the universe still holds extremes beyond our intuitive grasp. And this is only the beginning of the story. If Chapter 1 was about scale, Chapter 2 is about limits. Because once you truly grasp how enormous Stephenson 218 is, the next question becomes unavoidable: how is this even possible? For decades, astrophysicists believed there were hard upper boundaries to how large a star could grow. These weren't arbitrary guesses. They were grounded in the mathematics of gravity, thermodynamic, and radiation pressure. According to our best models, stars above a certain mass become violently unstable. Their own energy output should literally blow them apart. And yet, here we are, staring at an object that appears to sit right on, or perhaps even beyond, those theoretical boundaries. To understand this tension between theory and observation, we need to look at one of the most important concepts in stellar physics, the Eddington limit. Named after British astrophysicist Arthur Eddington, this limit describes the point at which the outward pressure from a star's radiation balances the inward pull of gravity. Every photon produced in a star's core carries momentum. When those photons stream outward, they push against the star's outer layers. In most stars, gravity easily keeps that outward pressure in check. But in extremely massive stars, radiation pressure becomes enormous. If luminosity climbs too high, radiation can overpower gravity and begin stripping material away from the star's surface. In simpler terms, there's a brightness ceiling. Cross it and the star starts to tear itself apart. Red hypergiants like Stephenson 218 operate dangerously close to that ceiling. They are bloated, unstable, and shedding mass at astonishing rates. Observations suggest that Stephenson 218 is losing material through powerful stellar winds, streams of charged particles flowing outward into space. These winds can carry away the equivalent of several Earth masses every single year. Over thousands of years, that adds up to a significant fraction of the star's total mass being expelled into the surrounding interstellar medium. And yet, despite this mass loss, the star remains gargantuan. One reason is that size and mass are not the same thing. This is crucial. Stephenson 218 is not 2,000 times more massive than the Sun. Its mass is estimated to be perhaps 30 to 50 times that of our Sun. Enormous, yes, but nowhere near 2,000 times heavier. The key difference lies in density. Red hypergiants are incredibly diffuse. Their outer layers are so expanded that the average density of the star can be far lower than the density of air at sea level on Earth. If you could somehow scoop a cup of material from the outer envelope of Stephenson 218, it would be more vacuum than substance. This is one of the strangest truths in astronomy. The largest stars are often the least dense. Imagine inflating a balloon. The rubber stretches thinner and thinner as the balloon grows larger. In a similar way, as massive stars evolve and exhaust their core hydrogen, internal changes cause their outer layers to expand dramatically. The core contracts and heats up as it fuses heavier elements, while the outer envelope responds by ballooning outward. The star becomes cooler at the surface, which gives it that deep red color. But its total energy output remains immense due to its sheer surface area. This is why Stephenson 218 shines with hundreds of thousands of times the luminosity of the Sun, despite having a cooler surface temperature. Luminosity depends on both temperature and size. Even if you lower the temperature, multiplying the surface area by billions more than compensates. But this creates instability. Inside the core of a star like Stephenson 218, nuclear fusion has progressed far beyond hydrogen. After hydrogen comes helium. After helium, carbon. Then neon, oxygen, silicon. Each stage requires higher temperatures and produces heavier elements. But there's a clock ticking. Every step burns faster than the last. Hydrogen fusion can last millions of years in massive stars. Helium fusion lasts hundreds of thousands. Carbon fusion may last only a few thousand years. Silicon fusion, perhaps mere days before collapse. When iron forms in the core, the game changes entirely. Fusion up to iron releases energy. Fusion beyond iron consumes energy. That means once the core becomes iron-rich, fusion can no longer support the star against gravity. Without outward pressure from nuclear reactions, gravity takes over catastrophically. The core collapses in a fraction of a second. In that collapse, temperatures spike to billions of degrees. Protons and electrons are crushed together into neutrons. The core stiffens abruptly, halting its collapse, and a shockwave rebounds outward. If conditions are right, that shockwave tears the star apart in a supernova explosion. For a brief period, the dying star can outshine an entire galaxy. Will Stephenson 218 die this way? Most likely yes, but there are uncertainties. Its current mass, after accounting for mass loss, will determine its fate. If enough mass remains in the core at collapse, the remnant could form a black hole instead of a neutron star. Given its scale, many astronomers suspect it will leave behind a stellar mass black hole, perhaps several times the mass of our Sun compressed into a region only a few dozen miles across. To appreciate how extreme that transformation would be, consider this: a star whose surface today would engulf Jupiter could eventually collapse into something smaller than Manhattan. That's the violence of stellar evolution. Now let's zoom out from physics and return to discovery. Stephenson 218 was not found by someone casually scanning the sky through a backyard telescope in Kansas or California. It required advanced infrared surveys capable of penetrating thick cosmic dust. The cluster it resides in, Stephenson 2, lies deep within the plane of the Milky Way in the constellation Scutum. This region is crowded with stars and obscured by interstellar dust clouds that block visible light. To optical telescopes, much of this area appears dim and unremarkable. Infrared astronomy changed that. Space-based observatories and ground-based telescopes equipped with infrared detectors allowed astronomers to peer through dust that would otherwise hide entire stellar populations. By analyzing infrared brightness and using spectroscopy, breaking light into its component wavelengths, scientists could determine chemical composition, surface temperature, radial velocity, and luminosity. Spectroscopy is one of the most powerful tools in astronomy. Each element leaves a unique fingerprint in the spectrum of light. By studying absorption and emission lines, astronomers can identify what a star is made of and infer its physical properties. In the case of Stephenson 218, spectral analysis confirmed it as an extremely luminous red hypergiant, but measuring its size required more than classification. Distance estimates had to be refined. If a star appears bright, that could mean it is intrinsically luminous, or simply closer than we think. Determining distance in our galaxy is notoriously difficult. Astronomers rely on methods such as parallax for relatively nearby stars, but for objects tens of thousands of light years away, indirect techniques must be used. Cluster membership helped. Because Stephenson 218 resides within a stellar cluster, astronomers could estimate the cluster's distance using multiple stars and statistical methods. Once distance was constrained, luminosity could be calculated more accurately. Then, using the Stephenson-Boltzmann law, radius estimates followed. Even with these tools, uncertainties remain. Stellar atmospheres are complex. Red hypergiants have extended envelopes that blur the definition of surface. Where exactly does the star end and the surrounding expelled gas begin? Measurements can vary depending on assumptions. That's why science treats records like largest star with caution. It's always the largest known star based on current data. And that brings us to an important philosophical point about astronomy. The universe is not obligated to fit our expectations. Time and again, discoveries have forced revisions of what we thought were limits. Pulsars were once unimaginable. Quasars shattered brightness assumptions. Black holes went from theoretical oddities to confirmed astrophysical realities. Each time we build better instruments, the universe surprises us. Stephenson 218 is one of those surprises. It suggests that under certain conditions, stellar envelopes can expand to extraordinary scales without immediate disruption. It hints that our models of mass loss, convection, and radiation transport inside extreme stars may need refinement. And it reminds us that even in our own Milky Way galaxy, there are objects we are only now beginning to understand. From a cosmic perspective, the existence of such giants also plays a crucial role in galactic evolution. Massive stars are factories for heavy elements. Without generations of stars like Stephenson 2.18 living fast and dying violently, the universe would contain little more than hydrogen and helium. The oxygen you breathe, the carbon in your cells, the iron in your blood, all forged in ancient stars that exploded long before the sun was born. In that sense, studying the largest star ever discovered is not just about spectacle. It's about origins. When you step outside tonight, whether you're in Florida humidity, under the clear skies of Colorado, or near the bright lights of Chicago, remember that somewhere toward the constellation Scutum, hidden behind dust and distance, a red hypergiant is nearing the end of its brief, brilliant life. Its outer layers are drifting into space. Its core is inching toward collapse. And though it is 20,000 light-years away, the story it tells is directly connected to ours. Because the atoms that make up your body were once inside a star. And somewhere in the distant future, long after humanity is gone, the debris from Stephenson 2.18 may help form new worlds, new suns, and perhaps even new life. The largest star ever discovered is not just a record holder.